Hello and welcome to the first in a series of videos about noise. In this first video I'm going to discuss what I mean by noise, play one example of a noise waveform, and start to look at how we can use mathematics to describe noise. Noise is a random signal, by which I mean that it's not possible to predict the value of noise at any point in the future. But it is a very important part of electronics because it limits the performance of many electronic circuits. When we think about noise, we often think about something that sounds a bit like this. That's an example of a type of noise called Gaussian white noise. And I'll be talking in future videos about what I mean by Gaussian and white in the context of a noise signal. Now, I mentioned before that an essential characteristic of noise is that it is unpredictable. You cannot exactly determine in advance what the value of noise is going to be. If you could always generate an equal and opposite voltage and then cancel out the noise from the incoming waveform. And you cannot get rid of noise that easily. Noise has an essential random element. But we can use some mathematical techniques to describe noise. We cannot work out exactly what its value is going to be, but we can determine what the probability is that it will have any particular value at any particular time in the future. So we have to describe noise using these statistical techniques. We can talk about probability distributions of noise, about the average value of noise, about the average power in a noise waveform. We just cannot produce a formula which will predict in advance what the actual value of the noise is going to be. Only the probability that it will have a particular value. Noise waveforms do have an amplitude, which we can describe as either a zero to peak amplitude or a peak to peak amplitude, and they have a power. And the average power in the noise waveform, like the average power in any other waveform, is proportional to the average value of the square of the voltage. So for noise signals, just like any other signal, to work out the average power, you take the values of the noise, square them, take the average value of that, and that gives you the average noise power. It's the square of the RMS value of noise. Now you may be wondering at this point, if we cannot predict exactly what the values of noise are going to be, how can we square those values, take the average value of the squares, and therefore determine the power? Well, the trick is taking that average. If we can determine the probability distribution of the noise, how likely it is to take any particular value, then we can work out an average value, and thereby the average power in the noise. And this is a very common and very useful way to characterize noise signals, because it turns out that with some very common types of noise, the peak-to-peak amplitude of the noise is in theory infinite. So we have here the case of a signal which has an infinite peak-to-peak value, but a finite value of power. It's all a bit strange, this world of statistics and noise, if you haven't come across these types of concepts before. But don't worry, we'll be going through them quite slowly in quite a lot of videos on this topic. For now, that's all I wanted to say about an introduction to the topic. Next time, I'm going to start talking in a bit more detail about what I mean by a probability distribution.